You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Cloud architecture refers to the design of systems and services deployed within cloud platforms, spanning everything from infrastructure to applications. It exists on a spectrum, beginning with fully on-premises environments, extending through hybrid models that combine local and cloud resources, and reaching multi-cloud strategies where multiple providers are used simultaneously. Each point along this spectrum offers benefits and challenges, particularly in terms of security. On-premises systems provide maximum control but require full management responsibility. Cloud platforms offer scalability and managed services but demand trust in providers. A sound cloud architecture balances flexibility, performance, and security while aligning with business goals. The cloud shared responsibility model is one of the most important principles for understanding cloud security. It defines the division of security duties between providers and customers. Providers are responsible for securing the underlying infrastructure, such as physical data centers, hardware, and foundational services. Customers are responsible for securing how they configure, use, and manage resources on top of that infrastructure. This model ensures clarity. Misconfigurations or poor practices on the customer side remain their responsibility, even if the platform itself is secure. Failing to understand this model often leads to breaches, as organizations assume providers cover more than they actually do. Provider and customer responsibilities shift depending on the service model. Infrastructure as a Service, IaaS, Platform as a Service, PaaS, or Software as a Service, SaaS. In IaaS, customers manage operating systems, applications, and data, while providers handle hardware and virtualization. In PaaS, providers also manage the runtime environment, leaving customers to focus on applications and data. In SaaS, nearly everything is provider-managed except for identity, user access, and data use. Security responsibilities narrow as organizations move up the stack, but they never disappear. Customers always retain accountability for access, data, and usage policies, regardless of model. Understanding these distinctions is vital for building secure architectures in the cloud. Identity and access responsibilities in cloud contexts are especially critical. Because cloud platforms are accessible over the internet, strong identity and access management (IAM) systems become the first line of defense. Customers must define who can access which resources, enforce multi-factor authentication, and monitor for misuse. Misconfigured IAM policies are one of the most common causes of breaches, as they inadvertently grant excessive privileges. Providers offer robust IAM tools, but customers are responsible for applying them effectively. Least privilege, just-in-time access, and periodic reviews ensure that identity remains both secure and aligned with operational requirements. In cloud, identity effectively is the perimeter. Secure network architectures in the cloud rely on virtual private clouds, VPCs, subnets, and security groups. These components mimic traditional networking controls but are software-defined, providing flexibility and scalability. Subnets divide environments into zones, such as separating web tiers from databases. Security groups and network access control lists, ACLs, filter traffic at both the host and subnet level. Designing secure architectures means carefully restricting inbound and outbound flows while still enabling business functions. Poorly designed networks often expose resources directly to the internet, creating unnecessary risk. Cloud-native networking provides powerful tools, but only if configured and monitored correctly. Data protection remains a shared responsibility, with customers playing a central role. Providers ensure storage infrastructure is durable and reliable, but customers must enable encryption, manage keys, and enforce backup strategies. Encryption of data at rest and in transit should be treated as mandatory, with key management services, KMS, supporting proper lifecycle handling. Backups should be tested regularly, ideally replicated across regions for resilience. Too often, organizations neglect their part of this responsibility, assuming the provider handles all aspects. Strong cloud architectures build data protection into workflows, ensuring confidentiality, integrity, and availability are maintained regardless of platform. Configuration management and drift detection are critical in cloud environments, where resources are provisioned dynamically and at scale. Secure baselines must be defined for services, and automated tools must enforce them continuously. Drift occurs when systems deviate from their intended state, often due to manual changes or ad hoc adjustments. In cloud, drift can expand rapidly because of the ease of provisioning. Configuration management tools and infrastructure as code (IaaS) frameworks allow consistency, while drift detection alerts defenders when systems stray from policy. Without these practices, security erodes invisibly. Strong architecture builds consistency into the very process of provisioning. Cloud-native services provide the building blocks for security architecture. Identity and access management (IAM) systems handle authentication and authorization. Key management services (KMS) manage cryptographic material. Logging platforms like CloudTrail or Stackdriver provide forensic records, while monitoring tools deliver real-time insights. These services represent core architectural elements, not add-ons. When integrated effectively, they provide standardized, scalable security foundations. However, they must be configured deliberately. Default settings are often permissive. Cloud-native services simplify many aspects of architecture, but responsibility still rests with customers to activate, align, and enforce them as part of their overall governance strategy. Multi-account or multi-project organizational patterns provide isolation across teams, departments, or workloads. Instead of placing everything into a single account, organizations separate environments by purpose, such as development, testing, and production, or by business unit. This prevents compromises in one environment from spreading unchecked. Accounts can be linked through centralized identity systems and consolidated billing, but remain isolated for security. Multi-account designs reflect segmentation at the architectural level, ensuring blast radius is reduced. This approach also improves compliance management, as sensitive workloads can be separated from less critical systems. Architecture choices here directly influence containment and governance outcomes. Tenancy models influence both cost and security in cloud designs. Single-tenant environments dedicate infrastructure to one customer, offering stronger isolation but higher costs. Multi-tenant environments share infrastructure among customers, reducing cost but requiring strict controls to prevent data leakage or side-channel attacks. Providers implement multi-tenancy safeguards, but organizations must evaluate their risk tolerance and regulatory requirements. Highly regulated industries often prefer single-tenant or hybrid models for assurance. Tenancy decisions become part of architecture, balancing security, performance, and economics. Understanding tenancy ensures that organizations align deployments with both technical risks and business realities in the cloud. Cost and security trade-offs are inherent in cloud architecture. For example, replicating data across multiple regions increases resilience but adds expense. Choosing single-tenant services may improve assurance but raises cost. Similarly, deploying advanced monitoring tools may add operational overhead. Cloud architecture forces organizations to evaluate how much risk they are willing to accept in exchange for efficiency. Strategic planning requires transparent discussions between business and security teams, ensuring decisions are risk-informed. A strong architecture is not always the cheapest option, but it represents a balanced compromise that sustains both protection and economic viability. Ultimately, cloud architecture is a combination of provider controls and customer governance. Providers deliver secure foundations, but customers must design, configure, and monitor their use. Identity, network design, data protection, and configuration enforcement all sit firmly in the customer domain. Governance processes ensure responsibilities are met consistently, with audits and automation providing oversight. Cloud adoption succeeds when organizations understand this partnership, using provider services effectively while maintaining accountability. Cloud architecture, therefore, is not outsourcing security, but rebalancing it, leveraging provider strengths while embedding governance to cover customer responsibilities across the environment. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Identity federation and single sign-on (SSO) integration are central patterns in cloud security. Federation allows organizations to extend their existing identity systems, such as Active Directory, into cloud environments without duplicating accounts. Single sign-on provides users with one set of credentials across multiple services, reducing password sprawl and lowering the risk of credential misuse. From a security architecture perspective, Federation centralizes policy enforcement and monitoring, while SSO improves usability and compliance with multi-factor authentication requirements. However, misconfigurations can create systemic weaknesses, as a single identity compromise may cascade across environments. Properly implemented, Federation and SSO streamline access while reinforcing strong governance. Secure secret management and key lifecycle practices are essential for cloud platforms, where applications frequently rely on tokens, certificates, and API keys. Secrets should never be hard-coded into applications or stored in plain text. Instead, cloud-native vaults or key management systems (KMS) must be used to generate, store, and rotate sensitive credentials. Lifecycle practices ensure that keys are periodically rotated, revoked when no longer needed, and logged for accountability. Automating these processes reduces human error and minimizes the chance of credential exposure. Secret management in cloud environments reflects the shared responsibility model. Providers offer tools, but customers must configure and enforce secure handling. Network segmentation and peering considerations extend traditional principles into the cloud. Virtual networks must be divided into subnets with security groups and network ACLs controlling access. Multi-account or multi-region environments require careful planning of peering connections, ensuring that only necessary traffic is permitted. Poor segmentation may allow attackers who breach one workload to pivot laterally across environments. Peering adds complexity, as it often bypasses perimeter controls if not carefully monitored. Architectures that enforce segmentation through zero-trust principles verifying traffic at each boundary provide resilience. Cloud design choices here influence not only performance but also containment of threats across accounts and geographies. Centralized logging and observability are crucial for maintaining visibility across distributed cloud environments. Each account, region, or service produces telemetry, and without aggregation, monitoring becomes fragmented. Cloud architecture should centralize logs into a single account or service, ensuring consistent retention and correlation. Observability extends beyond raw logs, combining metrics, traces, and context to reveal why systems behave the way they do. Cross-account aggregation supports incident response and compliance, providing unified evidence trails. Without centralization, blind spots emerge, undermining detection and forensic readiness. Architectures that prioritize observability treat visibility not as an afterthought but as an inherent design requirement. Automated policy enforcement tools, such as Cloud Security Posture Management (CSPM) platforms and Infrastructure as Code (IaaS) scanning, prevent misconfigurations before they reach production. These tools continuously check resources against policies, flagging or remediating issues automatically. For example, if a storage bucket is exposed publicly, CSPM can alert or close it before attackers exploit it. IaaS scanning evaluates templates to catch risky patterns early in the pipeline. Automation ensures consistency across fast-moving environments, reducing reliance on manual checks. Cloud architecture integrates these tools into pipelines, reflecting a proactive stance. Continuous enforcement transforms policy from guidelines into operational guardrails. Backup, recovery, and cross-region replication strategies ensure resilience against outages and data loss. Cloud providers offer highly durable storage, but customers must architect redundancy to handle accidental deletion, corruption, or region-wide failures. Backups must be encrypted, versioned, and tested regularly. Cross-region replication adds further resilience, ensuring that workloads survive even if a single data center is unavailable. Recovery strategies must also account for ransomware or insider threats, emphasizing immutability and quick restoration. In cloud contexts, resilience planning balances cost with protection, ensuring critical assets are available when needed most. Hardened cloud architectures always include backup and recovery by design. Secure API gateways and service meshes provide workload isolation and control in cloud-native architectures. API gateways centralize access, enforcing authentication, rate limiting, and monitoring of service calls. Service meshes extend this control deeper, encrypting communication between microservices and enforcing policies consistently. These tools reduce complexity for developers while providing security teams with visibility into distributed workloads. Without them, microservices may communicate insecurely, exposing data or increasing attack surfaces. API gateways and service meshes exemplify architectural controls that embed governance directly into application flows. By designing them into cloud environments, organizations enforce consistency and strengthen resilience against misuse or compromise. Container and serverless workloads bring unique security considerations in cloud-native designs. Containers require hardened host operating systems, minimal images, and strict isolation controls to reduce risk. Serverless architectures reduce patching responsibilities but shift focus to securing permissions, event triggers, and dependency management. Misconfigured functions can create unintended exposures, particularly when given excessive rights. Both models demand strong observability, as traditional network-based monitoring is less effective in ephemeral workloads. Cloud architecture must adapt by embedding controls into the runtime itself, recognizing that security shifts to the code, configuration, and orchestration layers. Hardening these workloads ensures agility does not erode security. Continuous compliance and policy as code practices bring governance into daily cloud operations. Compliance is no longer a periodic audit but a continuous requirement enforced by automation. Policy as code frameworks embed security and regulatory controls into deployment pipelines, ensuring every resource aligns with standards before creation. Continuous monitoring validates compliance after deployment, closing gaps quickly. This approach reduces human error and ensures consistent enforcement across environments. From GDPR to PCI DSS, compliance mandates are integrated directly into architecture, making adherence measurable and repeatable. By embedding compliance into the pipeline, cloud security becomes both proactive and sustainable. Vendor lock-in and portability considerations play a subtle but critical role in cloud architecture. Relying heavily on a single provider's proprietary services may create efficiency but reduces flexibility if requirements change or risks emerge. Portability strategies, such as using containerization, open standards, and abstraction layers, preserve the ability to migrate workloads across providers. However, portability often comes at a cost, such as reduced performance or higher complexity. Architecture decisions must weigh these trade-offs, balancing efficiency with resilience. Planning for portability ensures that organizations retain long-term freedom, avoiding dependency risks while still leveraging the strengths of cloud-native services. Incident response responsibilities in cloud environments require careful coordination between customers and providers. While providers secure infrastructure, customers remain responsible for detecting, containing, and remediating incidents in their accounts. Clear escalation procedures with providers are essential, especially when forensic data or service-level interventions are needed. Shared responsibility does not end at prevention, it extends into coordinated response. Cloud architectures must plan for this by embedding monitoring, centralizing evidence, and establishing communication channels with providers. Effective incident response depends on clarity, ensuring no gaps exist when rapid action is needed during an attack. In conclusion, cloud architecture is a collaborative responsibility that requires tooling, governance, and continuous oversight. Providers supply resilient infrastructure and robust security services, but customers must design, configure, and monitor them responsibly. Identity federation, secret management, segmentation, observability, and compliance all reflect shared duties. Automation ensures consistency, while portability planning protects long-term flexibility. Incident response depends on coordination between parties, reflecting the integrated nature of cloud ecosystems. Cloud security succeeds when architecture unites provider capabilities with customer governance. Together, they create scalable, resilient systems that support business growth while resisting threats in a dynamic environment. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.